In this part of the operating systems course related to paging approach in memory management, we will cover local and global frame allocation policies. We will cover also working set model and thrashing. For frame allocation in page replacement, the following policies may be followed. In global replacement, a process can replace any page in the memory. However, in the local replacement, each process can replace only from its own reserved set of allocated page frames. Here there's an example to show the difference between local and global page replacement algorithm. Here we have three different processes. Process A, which has pages A0 up to A5 in the memory. Here is the process B and process C. And together with the pages, we have also information about the age of the processes. Here, this value is showing, for example, when this page is loaded into the memory. Or it may be a timing about when this page is referenced. For example, if we are going to apply first in, first out, in that case, suppose that these are the times at which the pages are loaded into the memory. And if we are going to use local page replacement, when a new page, for example, page 6 of process A, to be loaded into the memory, when there's a reference to that page and it is not in the memory, there will be a page fault, and we have to choose a victim among the pages belonging to the process A. And they consider the times given here, and this page is the oldest one. By the first in, first out local replacement, we are choosing this page as the victim. It is removed from the memory, and the new page of the process A is loaded instead of that page. However, if this was going to be a global replacement algorithm, in that case, we have to consider all the pages belonging to all the processes and check which one is the oldest one. This is loaded at time 2, for example. This is the oldest page in the memory. Then this is chosen as the victim. It is removed from the memory. And instead of this frame, instead of this page, B3, process A, page 6 is loaded. This is global page replacement. In case of local replacement, operating system should determine how many frames should be allocated to each process. The number of frames for each process may be adjusted by using two ways. The first one is equal allocation. If there are n frames and p processes, then n divided by p, and then the integer is taken, frames are allocated to each process. In the proportional allocation, let virtual memory size for a process P be VP, and let m processes and n frames in the system. Total virtual memory size is the summation of the virtual memory size of each process. And then allocate the virtual size of the process divided by the total virtual memory size multiplied by n frames to process P. For example, consider a system having 64 frames. Assume 4 processes with the following virtual memory sizes. Virtual size 1, this is the virtual memory size for process 1, is 16. It is given as 16. virtual 2 is given as 128, virtual 3 is 64, and virtual 4 is 48. In equal allocation, operating system allocates, and here n is 64, divided by p, we have 4 processes, so 16 frames to each process. Notice that in equal allocation, the sizes of the processes are not considered, even though a process, for example, only 4 pages, it is assigned 16 frames. In the proportional allocation, the size of each process is taken into account when the frames are allocated. First, virtual memory size, total virtual memory size, which is the summation of the virtual size of each process, is calculated. So here we have 16 plus 128 plus 64 plus 48. This makes 256 pages. However, we don't have that much page. We have only 64 pages. Then consider the size of process 1, virtual size, divided with the total virtual memory size, and then multiply it with the memory size, which was given as 64 frames. So if these operations are applied, we have 4 frames to process 1. For the second process, virtual memory size is 128, so the result is 32. 32 frames are assigned to process 2. The virtual memory size for process 3 is 64. 64 divided by 256, total virtual memory size multiplied by number of frames. 16 frames are assigned to process 3. And for the last one, 48 divided by total virtual memory size multiplied by number of frames, we have 12 frames to be assigned to process 4. Let's continue with thrashing. A process is said to be thrashing if it is spending more time for paging in out due to frequent page falls compared to its execution. Thrashing causes considerable degradation in system performance. If a process does not have enough number of frames allocated to it, it will issue a page fault. A victim page should then be chosen, but all pages may be in active use. So victim page selection and new page replacement will be needed again in a very short time. This means that another page fault will be issued shortly, and so on and so forth. In case a process thrashes, the best thing to do is to suspend its execution and swap out all of its pages in memory to the backend store. Local replacement algorithms can limit the effects of thrashing. If the degree of multiprogramming is increased over a limit, processor utilization falls down considerably because of thrashing. Normally, as the degree of multiprogramming increases, we are expecting the processor utilization to increase and then saturate. However, if the multiprogramming degree is beyond limits, then thrashing occurs and the processor utilization starts to decrease. In that case, the degree of multiprogramming should be decreased by suspending some of the processes. This figure is showing how page fault rate changes as a function of the number of page frames assigned. Here we have two thresholds, A and B. As the number of page frames assigned, notice that the page fault rate is decreasing. Here we have two thresholds, A and B, and here if the number of page faults is larger than this threshold in this region, we may think as if the system is thrashing. So the multi-programming degree should be decreased, and as a result of that, some of the processes are suspended and the number of page frames assigned to each process is increased. There is another region here. The number of page frames are so large that almost no page fault occurs, but this may not be necessary because in this case, the multi-programming degree may be very small unnecessarily. Instead of that, we may keep the operation region between A and B, so we have a good multi-programming degree and good page fault rate. To prevent thrashing, operating system provide a process as many frames as it needs. For this, working set model, which depends on the locality model of program execution, can be used. We shall use a parameter delta, which is called the working set window size, and examine the last delta page references. The set of pages in the last delta references is to be called the working set of a process. Assume that delta, which is the working set window size, is set as 10, and it is required here to calculate working set and working set sizes at every 5 seconds. Suppose that currently we are at this point in time, and these are the previous page references. If there are more than one reference to the same page, they are considered also. Window size is 10. We are considering the previous references in the window. Time is 10. We are at this time. The working set is 2, 1, 5, and 7. We have these pages in the working set. And because the number of different pages is 4, the working set size is 4 times T10. And then some other page references occurs. And 5 units of time later, we are considering the new window. And in this window, having size 10, we have these pages. So the different pages in the window are 7, 5, 1, 3, and 4. So this is our current working set at time 15, and working set size is 5. Again, time passes for a period of 5. Time becomes 20, and we have to consider the new window. Here in the window, for the last 10 references, because delta is 10, we have the references to pages 3 and 4 only. So working set size is 2 for this process. And notice that for this part of the execution, if this process was given 2 frames, it would be enough. However, in the previous window, working set size was larger, then in that time, the need was larger than the last case. Note that In calculating working sets, we do not reduce consequent references to the same page to a single reference. Note that in calculating the working sets, we do not reduce consequent references to the same page to a single reference. Choice of delta is crucial. If it is too small, it will not cover the entire working set. So the calculated working sets will be smaller than the actual working sets. If it is too large, several localities of process may overlap. In that case, whatever calculated as the total virtual memory will be larger than the actual virtual memory. It should be chosen well. It is suggested to be about 10,000 references. Now compute the working set size for each process and find the total demand D of the system at that instance in time as follows. Demand for the current time is the summation of the working set size of each process. I is from 1 to P, this is the number of processes currently. If the number of frames is n, then if D is larger than n, say that the system is thrashing. If D is less than n, the system is all right. Hence, degree of multiprogramming can possibly be increased. Notice that if the window size is not chosen correctly, for example, if it is too small, then the demand will be less than the actual demand value. Because of that, although the demand is not less than n, it may be observed that it is less than n, as if it is less than n, and the multiprogramming degree may be increased according to this rule. However, in fact, it may result in thrashing. And for the case if a window size is larger than necessary, in that case, unnecessarily, demand may be calculated larger than n, and it may thought as if the system is thrashing, multiprogramming degree is decreased. However, in fact, it was not thrashing. To be able to use the working set model for virtual memory management, operating system keeps track of the working set of each process. It allocates each process enough frames to provide them with their working sets. If at one point, if demand is larger than n, operating system selects a process to suspend. The frames that were used by the selected processes are reallocated to other processes. Page fault frequency can also be used to decide on decreasing or increasing the number of frames allocated to a process. In the working set, the set of pages used by the k most recent memory references. Therefore, the working set is a function of k and t. This is the size of the working set at time t. If we increase k, so this is the window size, we expect that the working set size to increase. However, if this value is large unnecessarily, that means that not only the current locality, also the past localities are considered unnecessarily. Now we are going to consider working set algorithm. To implement working set model, it is necessary for operating system to keep track of which pages are in working set. An algorithm may be when a page fault occurs, find the page not in the working set and evict it. Evict means that choose that one as the victim and remove from memory. To implement such an algorithm, we need a precise way of determining which pages are in the working set. In the working set algorithm, we have a virtual clock which ticks periodically. Assume that the current value of the virtual clock is this one. In the page table, in addition to the frame numbers showing where the page is loaded in the physical memory, we have some additional information. Here, the value written here, time of last use of that page. And also, we have a reference bit. It is showing the page is referenced during this tick if the value is 1. And if it is 0, it means that page not referenced during this tick. If we are going to choose a victim, scan all pages by examining R bit. If R is 1, set time to the last use to current virtual time. If R is 0, and if this age, calculated as the difference of the value here and the current time, if the age is greater than a threshold value, then remove this page from the memory. However, if reference bit is 0, but age is less than threshold, remember the smallest time. Working set clock algorithm is a version of the working set algorithm. In the working set clock algorithm, the data structure needed is a circular list of page frames, as in the clock algorithm. Initially, this list is empty. When the first page is loaded, it is added to the list. As more pages are added, they go into the list to form a ring. Each entry contains the time of last use field from the basic working set algorithm, as well as the R bit. This is the reference bit. Here it is shown in the figure. And also the modified bit. It is not shown here. As with the clock algorithm, at each page fault, the page pointed by the hand is examined first. If R bit is set to 1, as shown in A here, the page has been used during the current tick, so it is not an ideal candidate to remove. The R bit is then set to 0, the hand advanced to the next page, and the algorithm repeated for that page. The state after this sequence of events is shown in B. Hand is showing this page. It is referenced in the last time, so hand is progressed to the next one. If the page pointed has R value as 0, as shown in figure C here, if the age is greater than the threshold value and the page is clean, it is not in the working set and a valid copy exists on the disk. The page frame is simply claimed and the new page put there as shown in part D. So this is removed because it is not modified and it is not referenced. And also the age is larger than a threshold value. This is removed from the memory and instead of that, new page is loaded. This is the current time and also the reference bit set to 1. On the other hand, if the page is dirty, it cannot be claimed immediately since no valid copy is present on disk. To avoid a process switch, the write to disk is scheduled, but the hand is advanced and the algorithm continues with the next page. After all, there might be an old, clean page further down in the line that can be used immediately. If we consider all the page replacement algorithms we considered so far, here there is a summary. If we consider the optimal page replacement algorithm. It is not implementable, but useful as a benchmark. Not recently used algorithm is very crude approximation of the least recently used algorithm. First in, first out algorithm might throw out important pages. It is easy to implement, but this may be a disadvantage. Second chance algorithm brings a big improvement over first in, first out algorithm. Clock page replacement algorithm is a realistic page replacement algorithm. Least recently used is excellent, but difficult to implement exactly. Not frequently used is fairly crude approximation to least recently used. Aging is an efficient algorithm that approximates least recently used well. The working set model somewhat expensive to implement. Working set clock is a good, efficient algorithm.